Hello, humans. If there are any humans. It's good to get Twitch notification that I'm streaming. Okay. Hello, human. Yep. Jose, are you back home now? I know when I don't even remember what day that was when I ran into you. But I know you were going back somewhat soon. Okay, gotcha. You're just off campus. Gotcha. That's right. You found a place to stay. Home's far, I guess. Eddie? Clark? Hey. Yeah, for sure. You can definitely ask questions in voice chat. That's where it probably is also useful to have headphones if you have them so that I don't hear myself coming in like 7 seconds later. Yep, I can hear you. And I couldn't hear myself, so perfect. Okay, so we have like half the people here. Let's give it another minute. Okay, now more people are showing up. Alright, so I guess the assignment for today was pretty chill, just because you guys had the test to work on. Hopefully that's going alright. If you have clarification questions, like after class would be a good time to catch me. I also have office hours for us from 2 to 3 today, so I'll be like hanging around Discord if you want to just grab me. You can like work together in the voice channel, or I can come in. Like that's time where I could easily share my screen and talk through things. So that would be good. If you have questions on your project as well, I am happy to help on that. I think all of them are pretty interesting, from my perspective. So I am definitely happy to talk about them if you're having trouble finding good references. Because it's not just finding a reference, right? It's also finding one that's at the right level. Because if you find like a graduate textbook, like that's probably not going to be as useful as finding something that's more like, okay, what's an introduction to this? And then once I understand a little bit more, I can dig deeper. But I can help with references. I can help you, if you feel like there's 20 directions you could go, I can help you kind of choose one or outline your thoughts a little bit. So just let me know. And then maybe after we talk about the first problem and hopefully have a few more people, I want to talk briefly about next. So on Friday, Dr. Ansaldi is going to give us a little spiel about why you should consider taking Algebra 2 next fall, since you've got class signups coming up here. And I need to make sure everyone has Zoom, because that's probably the easiest way to do that. Just have like a quick Zoom call at the start of class on Friday or something. Okay, so let's get into it. So we started this last time, but we might as well go through both parts again, just because I don't know how well you remember how we finished. So here, right, we have a finite cyclic group. And so we'll just say, it's generated by some tiny little g guy. then I don't know why I capitalized that. Then for any m in Z, the order of g to the m, right, like every element in the cyclic group generated by G looks like g to the m, so we would like to know like what is the order of that in general without having to just do it multiplication over and over and over again until you get back to the identity. And so this order is exactly, cyclic of order n. So the order of little g is n. Then this is n over the GCD of n and m. I don't know why I put g. Sorry. N over the GCD of n and m. So basically, this is the smallest power of g to the m that gets you back to the identity. Okay, so first I just want to rename that, right? So like let d be the GCD of n and m, so I don't have to write so many letters. Then we want to gather what we know, right? And I guess, well, first we'll do the one direction that we did last time that was easy, and then yeah, we'll gather all the stuff that we know and see how we can put the pieces together. So going this way, or I guess our first thing, right, is showing that this actually is some power that gets us to the identity. Right, we want this to be E, and basically, I mean, this is just multiplication, right? So this is mn over the GCD of m and n, and then we just pull down the n, and then leave the m up top. So basically, they just switch roles. I don't know why I'm rewriting that and not just calling it D now. And so what is g to the n? Well, g had order n, so this is E. And so we're good. So it definitely is a power that gets us to the identity. The question is, why must it be the smallest one, right? So second, we must show that if g to the m to the k is equal to the identity, then d is smaller than k. Right? If. It's not a very good F. So we'll actually show something stronger. We'll show that d divides k. And that implies it's less or equal to. Right, because if you divide into it, you couldn't have been bigger than it. So that's actually easier here because we're not really dealing with addition stuff. This is all like multiplication, and so basically finding that it's a factor of k is much easier than just showing somehow that it's like less than or equal to it in some other way. So what do we know? Okay. So one thing, if g to the m to the k is E, right, which is our assumption, then you can gather it down, so g to the mk is E, and therefore, by one of our theorems, right, that since n is the order, n must divide mk. Alright? And then we need some relation with D, but what is D? So D is the GCD of m and n. So in terms of like what does this mean to be not even just the GCD, but just like a CD? How can I state this in terms of divisibility? What do I know must be true about D with regards to m and n? Yeah, it divides both. So D divides M and D divides N. Okay, so again, writing just like divides is not the most useful. We like to rephrase this. So n divides mk. That means that mk is n times, I don't know, some L, for some L and Z. M or D divides M, right? So M is D times, I used M prime. You can use whatever you want. I'm just starting to run out of alphabet here in this little area of like I, J, K, L, M, N. So I just said these things. But you can write whatever you want. The point is, D is a factor of N, D is a factor of M, and N is a factor of MK. And then what do we want? Right, we want to show that D divides K. And so the idea here, right, so we want D divides K, or K is equal to D times, some Q, where Q is in Z. These would be equivalent. Right, and so the idea is M and N share this greatest common denominator, and then once you have this K here, you can essentially divide each side by D, right, the greatest common denominator, and then you'll get the N over D, which is N prime, right? Look back at what we want up here, right? This order, this is N over D, so we would get the N prime divides K, and oh yeah, we don't want D divides K, do we? Sorry, we want this power. We want N over D. I'm sorry. Then N over D. Right, everything else, right? It's the order, not the GCD. So, sorry, N over D divides K, and which implies N over D. Sorry, since I had to backtrack there, does that make sense? What we just did, I just was screwing up what we had earlier, right? We want the GCD in the denominator, right? It's N over the GCD is our order, so that's what we want to show is less than or equal to K. Okay, yeah, sorry about that. Yeah, because the idea, right, is you divide out this greatest thing, and then they essentially will not share anything else once you divide by that. So let's just rewrite what we have, right? So we want K to be divisible by this, so we start with the MK equals NL, and then the idea is just to use these two guys to rewrite, right? So in terms of D, because we somehow want D to show up here so that we can divide by it, right? So we have D M prime K is D N prime L, and then we just divide by D on each side, right? So divide by D, and then you get M prime K is equal to N prime L. And sorry, so I didn't, back in terms of what I want, I have to restate that too, right? So I want, right, so we want that K divides, that N over D divides K, and we have now named N over D N prime. And so what we want is K is equal to some M prime times something. So why is this true here? Well, we have K, and then we have N prime times something. So how can we actually conclude that N prime divides k here, since we don't have k, right? We have k times n prime. So like y must n prime divide k here. Right, because it divides a product. Why does it have to divide that specific half of the product? Does anyone see why that should be true? How do you know that is an integer, right? If you're dividing by m prime. Right, so I agree. You could solve for k and get n prime L over m prime. But then like why do we know this is an integer? Think about how we have defined d here. This is very important to think about what we actually divided by. But integer over integer may not be an integer, right? You could have like 3 halves, for instance. Yeah. So it's very important that we divide it by the greatest common denominator. So let me ask you this. Do m prime and m prime share any factors? Are you sure? Exactly. No, because we divided by the GCD, right? So remember, we had GCD of m and n is d, and then basically we just divided both of them, right? So m prime is equal to m over d, n prime is n over d. Whatever common factors they had, we just removed by dividing by d, because it's the greatest one, right? So if they had any factors left over, well, that just would have been lumped into the GCD. So dividing by the GCD removes all common factors. Right, so the GCD of m prime and n prime is 1. Exactly, exactly. And so now, if we go back up to what we had, right, we have m prime k equals n prime L. So if we see this, and we want n prime divides k, right? So clearly n prime divides m prime k. But the point is, it shares no common factors with this. So n prime shares, yeah. I don't need to say that again probably. What I have written up above, right? That's the eraser. GCD, right? So yeah, what I have written here is the key, right? So it shares no factors with n prime, but it divides the whole thing. So all of its common factors lie with k. I mean, I don't know if anyone else is having issues. It's fine on both of my monitors, and OBS says I'm not dropping any frames or anything, so I don't know. That's really weird. An error occur while trying to play this content. Yeah. I'm not sure, Menzel. I'm sorry. I don't know if it has to do... Is this the same thing you've been using to watch Twitch before? Okay, cool. Sorry, so does this step make sense? So seeing that these share no common factors, so that basically none of the common factors are with this, they all must be with k, and so n prime divides k. Does that make sense? Okay, cool. Yeah, and you can see it with like some examples as well, right? Where, I mean, just basically pick a couple of things. So, like 3 divides 18, and you can write 18 as, 2 times 9. And so like 3 and 2 share no common factors. Or you can even do something bigger, right? Let's do it so that it's actually bigger than 3, so at least have a chance. So let's say 36, and so it's 4 times 9. So here, like, the GCD of 3 and 4 is 1, and so, like, all of the 3's go into just this second part, right? So that's kind of the idea. Okay, so before we move on, this is something I mentioned at the very start. Now that I see we have more viewers, hopefully everyone is here. I wanted to ask, so the idea here is Dr. Ansaldi wants to briefly talk to you guys. Wants to talk at the start of class Friday. About Algebra 2. Basically, it would be a follow-up to this class, but a little bit different. So I think her plan is basically to talk about polynomials and like all the stuff you can do with them and do it from a more like computational approach. So, I mean, obviously it'd be different than like dealing with polynomials and like calculus or whatever, but, like solving roots of polynomials and stuff like that using abstract algebra techniques, basically, which is one of the main reasons that group theory and like abstract algebra came about at all, was basically figuring out stuff with polynomials. That was actually like a huge motivation historically. So basically, it would be easier to not have her like have to come into our Discord and like share a screen or come on Twitch somehow when she's not in my office. So my question is, do you have Zoom? And so maybe type 1 in chat for yes and 2 for no on Twitch chat. I just want to get like a poll, because the idea is to start class with like a very brief Zoom chat and then come on over to this. Okay. F for respects. For the boys. Alright, I know that I have 12 viewers. There's got to be more people than this. It's half of the people. I see no 2s. Alright, well, I'll just put it in chat myself, and then if you respond later, 1 in chat for, or how about type in chat 1 if you have Zoom and 2 if you don't. Okay, cool. That works for me. So I'll send info about that. So just try to make sure basically that you're on time Friday, but I'll send out an email, and then I'm sure she'll send out like an actual invite. There should be a chat. You can just respond in here, Mansell. Discord's fine too. And I got you, Jose. Cool. All right. So then I did not assign 446. Again, this is at least one of the directions is a little time consuming, although there is a hint at the bottom of the page. I just thought, that time would be better spent on the exam. So that's perfectly fine. I will go through it. So I did have you do 447, which is kind of applying what we just did, right? Order of elements. But then 446 is nice too, and especially it's nice in regards to 449. Basically, like if you want to figure out a subgroup lattice and figure out like, okay, I have these things that are in the same subgroup, like do they both generate it? Does one generate it and the other one generates a smaller guy inside? How do I know, right? So you might want to know when two powers of your G generate the same thing. And so this is how you figure that out. So we've got G, order of G is in, this isn't in order. It's generated by little g, so it's finite cyclic of order n. And then the claim is that you see two powers are equal, or they generate the same group, if and only if their GCDs with n are the same. K and n. So one of these directions is very easy. Which one? Right to left or left to right? You should be able to use what we just did for at least part of this. Left to right, or like going right? So I actually think the other way is going to be well, so that means they have the same order. The question is like, why would they then be equal, right? Left to right is going to be a little bit easier because if these are the same, then they must have the same order. So here we want to use 445, right? So if these guys generate literally the same group, then they have to have the same order. And by 445, what is this? Well, so we have n divided by the GCD of m and n equals n divided by the GCD of k and n. Well, you can like cross multiply, divide, but basically the point is these GCDs must be equal. Right? So that's the easy direction. The other one is a little bit harder. So there's the hint down below, basically, that like one of the containments is very easy, but in general, it's a little bit harder. But it kind of boils down to what we showed in proving that subgroup of cyclic groups are cyclic, right? That it's generated by like the GCD or G to the power, the GCD of like all the positive powers that show up. That's basically the idea here, right? So for this, the goal here, show that in general, this guy is actually generated by the GCD of m and n. And so once you show that these are the same, so once we show this, then if the GCDs are equal, then we get g to the m equals g to the GCD of m and n, but then that GCD would be equal to the GCD of k and n, and that guy would be the group generated by g to the k. So basically, once we show this, we would be done pretty quickly. Does that make sense for what our goal is then? Cool. Okay, so we will try to show both containments. So this is what we want. And I'm going to say D again, where D is the GCD of m and n, just so I don't have to write it. And so, yeah, one direction is easier than the other, right? So D divides m. So g to the m is equal to g to the d to the q, right, for some q. Thus, anything in the subgroup generated by g to the m, if you have g to the m to the k, is equal to g to the d to the k times q, which lies in the subgroup generated by g to the d. So this direction is pretty easy. Basically, one is a power of the other, so it is definitely contained in that subgroup. The other direction requires more work. Right, and so here we need to show anything in the subgroup generated by g to the d has to lie in the subgroup generated by g to the m. And so here the hint is given to use Bezout's lemma. So this is something I mentioned earlier. I didn't say its name, I don't think I call it Bezout's lemma, but basically if the GCD of m and n is d, similar to, I definitely say it for like equals 1, I said it can be generalized to d. So this is true if and only if there exist x and y in z such that mx plus ny is d. Right, and so if they're relatively prime, if they have GCD 1, then d would be 1 here, and that's the one that we've already used previously. Okay, so why does this matter? Well, we can now say, right, that g to the d is g to the mx plus ny, which can be split up. And then how can I rewrite this? Why is this nice? Why am I basically done now? What do you mean take out the d? I think there's a faster way here. We're not using something that is given in the problem. What's the order of g? Where is this? Way up here. Yeah. Remember that the order of g is in. So what can we say down here? Yep, it's order n. So why does this help us here? Yes, exactly. There we go. Yeah, so this guy is equal to e, right? Because it's g to the n to the y. And so this is equal to g to the mx, which is g to the m to the x. So now we know that g to the d to the k is g to the m to the x times k. And so we get the other containment. So these guys are equal. So this is useful, and we'll see how when we talk about 49. It gives us a little faster way to like tell what is going to be redundant when you have like a whole list of things that you don't have to check like every friggin' element. Okay, let's do it. So 447. Someone want to what are the orders here? So this is in an order 12 group that is cyclic. And we had these three powers. Yep, this is order 6, right? It's 12 over the GCD of 2 and 12, which is 2. So we get 6 by 45, 445. Good. Yep, 12 over the GCD of 8 and 12. Yep, yep. So this one has GCD 1, and so this is 12. And yeah, as I saw from Tyler there, then we had 12 over the GCD here, which is 4, and we get 3. Good. No worries, Clark. Yeah, so that 445 makes this really easy, right? So you don't want to go through. I mean, you could, right? This isn't a huge group, so you could do like g squared, g to the 4th, g to the 6th, g to the 8th, g to the 10th. Now I'm back to e. So I went 1, 2, 3, 4, 5, 6. So it's order 6. But you can imagine if I asked you to consider a cyclic group of order 104 and asked you for the order of g to the 8th, you probably don't want to actually do that, right? You want to just see how it divides, quickly use this formula, and figure out what the order is. Or g squared. 57 times to multiply it out sounds awful. Which elements generate g? So clearly it's generated by g itself. What else generates it? Yeah, so we just saw g to the 7th generates it, right? Anything else? G to the 5th? Yep. Whoops. Yep, g to the 1st, g to the 5th, and then I think we're missing 1, which you could get in one of two ways here. You could either look for the last one that has GCD 1, or the fact, yeah, exactly, or the fact that this is the inverse, right? These guys are inverses, and these guys are inverses. So once you have one, you immediately get the other ones, right? And notice that these are exactly the elements in U12, right? These are the powers in U12. Because these are exactly the things that are relatively prime with 12. Hey, Borkman Bork. Cool. So 448 was a pretty quick corollary here, right? So we've got another finite cyclic case, which is basically everything that we've had for today's class. And then the claim, right, is that G, the group is also generated by some kth power of G if and only if the GCD of n and k is 1. What is this accord, like, how does this follow? This should be a one-line proof using what? You could do it the long way, but you should be able to cite something. You 46, yeah, 46 is the one you want. Yep. So I guess, I mean, 45 also works, that you would get that they're all order n. The issue, yeah, I mean, it does, it immediately follows from 46 though. It would be like 2 lines if you use 45. Immediately from, prepositions are good. Immediately from 446, right, where m is 1 in that statement, right, because the GCD of 1 in n is most definitely 1, and then this would be the result, right? Okay, so then the other one that I had you do, which this is where I would love to see a shared screen, because there's no way you're putting this in Twitch chat. So I guess the first part's easy. You can definitely do that, but it's hard to do a subgroup lattice in Twitch chat unless you're very, very talented. So what generates, so this is Z18, right? So we're in addition here, but it's cyclic of order 18. What elements generate Z18? So obviously, again, everything relatively prime, but what are those things? Yeah, 1, 5, 7, 11, 13, and 17. And can I explain what it is? Yeah, so this is everything up to 17 under addition. The operation is addition modulo 18. Right, so these are like all remainders, and so if you want to figure out what the element is after adding, right, so like 16 plus 12 is 28, but that's not in that set, but 28 has remainder 10, right, so it would be 10 mod 18. Yeah, and so how are we finding these elements? Again, just to kind of reiterate, like the way I usually think about this, right, is 18 is 2 times 3 squared. I think in terms of the primes dividing it. And so I have a 2 here. So if I want GCD 1, it has to be odd. And then it can't be a multiple of 3 either. And so that's how you get these, right? You immediately throw out all the evens, and then you throw out 3, 9, and 15 because they're multiples of 3. And this is what you're left with. So that's how I usually think about it. So throw out evens, throw out multiples of 3. Okay, and so for the subgroup lattice, this can take some time, right? So we know that these guys all are just going to generate the whole thing. So these we don't really need to consider. So basically we're looking at the subgroups generated, and remember, so this is important. So why does it suffice to look for subgroups generated by one element? Yeah. Why do we know that all the subgroups have to look like this? Why is this enough? Right, because in some big groups, even abelian ones, you may have subgroups generated by many elements. Why do we know these have to look like this? We have a nice result that we are using here. Any ideas? I mean, you could do it, but we can hit it with a little bigger hammer. This is our big result from last time. I mean, yes, they are all cyclic, but like, why must they be cyclic? So our whole group is cyclic, right? Z18 is cyclic. What do we know about subgroups of cyclic groups? We know they must all be cyclic too. And this was our theorem from last time. So this is an important one to remember, right? If you have a cyclic group, every subgroup is cyclic. So therefore, we don't need to worry about things generated by more than one element. We know everything has to be generated by one. And so this means that subgroups, so I guess, sorry, our potential proper subgroups, not even potential, we know they're proper because we found the ones that were not. So proper subgroups generated by, I mean, we have the long list, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16. All right, there we're done. So I don't want to go through all of these. I don't know about you guys. It sounds terrible. So how do we quicken the pace, right? So this is where we can use 446 to figure out when we are going to get repeats, right? Things that are redundant. So let's look at 2, for instance. So this gives me all of the evens, right? So this is 0, 2, 4, up to 16. It gives me all of the evens. What other elements in here will generate the same group? So what elements in this also generate this? Well, we know that 2 is equal to, say m, this is 446, right? 2 of those, yes. Inverses. So inverses is a quick way to get one element, but we want, right, so I mean that tells us that 2 and 16 will definitely generate the same thing, but there's going to be more than just that here, right? So we have a bigger result now with 446. So, right, we're looking for things that have the same GCD as 2. And so in this case, right, like that is equal to 2. GCD of 2 and 18 is 2. Yeah, exactly. So all the other elements with the GCD of 2. So you start going through the list, right? So again, 18 is 2 times 3 squared. So for the GCD to be 2, you're looking for even numbers that are not divisible by 3. So basically, everything except 0, which is a multiple of 3, 6, which is a multiple of 3, and 12, which is a multiple of 3. Right? These are our multiples of 3 inside this subgroup. So basically this tells us immediately now that these guys are all equal. And so we don't have to check any of those. They're all lumped into the same thing. This is very nice. Really reduces the workload. So I'm going to start, let's see. So then the next one that seems reasonable to check, right, would be either, well, do you want to stay inside here and do the subgroup generated by 6 versus the subgroup generated by 12, or do you want to go to the subgroup generated by 3? I'll leave it up to you guys. And this will be what we finished with, obviously. Yeah, we do have that too. Yeah, for sure. Let's just finish this one up. So, right, this is equal to 0, 6, and 12. It has order 3. Now the question is this the same thing, right? So 12 is inside. Is this the same as the subgroup generated by 12? Well, the GCD of 6 and 18 is 6, and the GCD of 12 and 18, well, that's also 6, right? So these guys are equal, and so we basically have 1/2 of this thing. So we've got like 2 over here, and we've got 6, and then of course we've got the identity down here generated by 0, and that's all we got there. And then you're right, Long. So we have subgroup generated by 3, right, which is 0, 3, 6, 9, 12, 15, and that's it. And we just saw that 6 and 12 generate something smaller, but the question is, does anything else generate something smaller, right? Well, the GCD of 3 and 18 is 3. This is also equal to the GCD of 15 and 18. But all the other ones have a higher GCD, right? So GCD of 9 and 18 is 9, and then the other two have GCD 6. And so basically that means that we have the subgroup generated by 3 is the same as the subgroup generated by 15, but then the subgroup generated by 9 is something smaller. So we have, over here, say, subgroup generated by 3, and then we've got the subgroup generated by 9, and then the subgroup generated by 6, right? This also lies inside 3 because 6 is a multiple of 3. So this is supposed to be like above. If that's not clear, this is not horizontal, right? This is very much going at least a little bit up. This is up, and so you get this kind of like, I don't know, diamond-ish shape, or I guess 2 adjoined diamonds. Yeah, 12 is the same subgroup as 6. Yeah. So this is just kind of a cool way to draw it. You don't have to draw it this way. But, right, these are all different orders. So this is like order 9, this is order 6, this is order 3, this is order 2, and this is order 1. Same subgroup for different generating set. Right, yeah, you would only write it once. Exactly, yeah. We only want to track subgroups, distinct subgroups. Yeah. Cool. Alrighty, so yeah, I'll send out information about Dr. Ansaldi talking to us for a little bit on Friday. And again, if you have questions about projects or clarifying stuff for the exam, I'll be in Discord for a little bit now, and I'll definitely be on from 2 to 3 during office hours. Alright? Have a delightful... Oh, why didn't we include 1? 1 is the subgroup that is the whole thing. Right, it is one of the generators. Alrighty, I will talk to you guys later.